In the heart of modern physics lies a dazzling and profound theory, quantum field theory, or QFT. QFT goes beyond the familiar world of particles and forces to reveal a deeper reality. It paints a picture of a universe teeming with invisible fields, like actors on a vast cosmic stage. QFT represents a grand synthesis of key ideas from quantum mechanics, classical field theory, and Einstein's special relativity. It reconciles the quirky world of quantum mechanics with the elegant framework of relativity. Imagine a world where particles are not isolated entities but rather ripples in a vast, interconnected web. That's the essence of QFT. Just as a ripple in a pond is a disturbance in the water, an electron is a disturbance in the electron field. QFT has been instrumental in shaping our understanding of the fundamental building blocks of matter and their interactions.
The crowning achievement of QFT is its embodiment in the standard model of particle physics. This model is our best attempt at describing the fundamental particles and forces that make up the universe. It's like a cosmic recipe book, listing the ingredients, or particles, and the rules for how they interact, which are the forces. Within the standard model, QFT provides a unified framework to describe three of the four fundamental forces of nature: the electromagnetic force, the weak force, and the strong force. It explains how these forces arise from the exchange of particles called bosons, which act as force carriers. Photons, for instance, mediate the electromagnetic force, holding atoms together. The standard model has been incredibly successful in predicting the existence of new particles, such as the famous Higgs boson. However, the standard model, despite its successes, is not the final word.
One of the most mind-bending concepts in QFT is the idea that particles are not fundamental objects, but rather excitations of underlying quantum fields. Imagine a still pond. Now imagine throwing a pebble into it. The pebble creates ripples that spread outward from the point of impact. In QFT, the pond is like a quantum field, and the ripples are like particles. Just as the ripples are disturbances in the water, particles are disturbances in the corresponding quantum field. For example, an electron is an excitation of the electron field, a photon is an excitation of the electromagnetic field, and so on. This concept has profound implications. It suggests that all particles of a given type, all electrons, all photons, are essentially identical because they are all excitations of the same underlying field.
A key concept in QFT is the idea of gauge symmetry. This concept provides a powerful framework for understanding the fundamental forces of nature. Imagine a circle. You can rotate the circle by any angle and it still looks the same. This rotational symmetry is a simple example of a gauge symmetry. In QFT, gauge symmetries are not about rotations in space, but rather about transformations in abstract mathematical spaces. These transformations leave the essential physics unchanged, just like rotating the circle doesn't change its shape. Gauge symmetries dictate how particles interact with each other by requiring the existence of force-carrying particles, the bosons mentioned earlier. The electromagnetic force, for example, arises from a particular type of gauge symmetry called U1 symmetry. Gauge theory, the framework built around gauge symmetries, has been incredibly successful in unifying our understanding of the fundamental forces.
Two shining examples of QFT's success are quantum electrodynamics, or QED, and quantum chromodynamics, or QCD. These theories describe the electromagnetic and strong forces within QFT. QED is one of the most precise theories ever devised, with predictions matching experimental results accurately. It explains how charged particles interact by exchanging photons. QCD describes the strong force binding quarks to form protons and neutrons, the building blocks of atomic nuclei. Both are essential components of the standard model, demonstrating QFT's power in describing fundamental forces.
Despite its triumphs, QFT faces a formidable challenge: incorporating gravity into its framework. The other three fundamental forces fit beautifully within QFT, but gravity remains resistant.
General relativity describes gravity as the curvature of space-time caused by mass and energy. It explains the large-scale structure of the universe but clashes with quantum mechanics at small scales. This highlights the need for a theory of quantum gravity to reconcile both.